我这儿应该是打开了，你那儿是绿的吗？喂，你那儿那个 OBS 里面那个播，可以是吧？可以的，可以的。他们直接看直播，直播啊，我看一下。Ici ou c'est bon? Merci. 啊？怎么说？啊？哦，行。
我觉得一切都行，太自然了。他是最懂事的啊，不愧是香港的。
可以的，可以的。
咱们这边人还没来呢。
我们先把那个 mute 掉，先把我们这个 OBS 里面 mute 掉。 Oui, oui, il est connecté. Mais il y a problème de connexion de mon micro ici. Juste une minute. Désolé, il y a problème de connexion BBB. J'ai essayé de reconnecter.
Ouais, moi j'essaie de me connecter, mais
Ok, je me suis connecté. Oui, mais il faut que les autres m'entendent. Ouais. Hello, hello, could you hear me? Yeah, I see that Stefan is speaking, but here I have no voice output.
moi j'entends.
Okay.
You want me to put the...
I don't know if here I have no output of voice. Wait.
It's working.
It's working? Okay. I see.
But the problem is that if we do that, you have to...
Yeah, I can put voice. Oh, sorry. And now I think it's good.
Yeah, we can.
We can work
It's
like
very low, but...
it's very low.
Maybe it's low because I have a USB microphone, so I decrease the quality. But
Yeah, I have a micro for the streaming, but here I have a micro of the PC for the BBB, and yeah, and I can hear you. I can hear you. It's the problem if you okay. And if could you hear me clearly? It's okay. And Zhongkai, it's okay?
yes.
Okay. Okay. Let's begin. I will. And,
moderator, c'est is it really connected, right? So somebody needs to approve my access. If you want me to be connected,
it's Boyang. If you are connecting, it's Boyang who organized.
I don't think it's really necessary. So
It's okay. I think it's approved. Okay.
So Adrian asked me to start. So I do my part. So hello everyone. Good afternoon. So we listened to Ziqiu's presentation. He includes defense out of his 3-4 years of work.
4 years.
Hard work, I guess. So let me start by introducing the jury members. So let me start by those who are present here. So Dr. Christian Jourier, inLarge research scientist from Lille, and he's a specialist in software robotics. Then I present myself. I'm Helen Seo. I'm CNRS researcher. I'm more on the geometric modeling and partially deep learning. Then we have those two who are connected online. They are two reporters of this thesis. So Professor Stefan Bordas from University of Luxembourg is somebody who is working on XFEM. Right? And Dr. Ziqiu ZENG from, so he's a research scientist at the Chinese Academy of Science in Hong Kong. I forgot what was his domain, but yeah, what is
Yeah, over rotation, I think.
Okay, and finally we have Adrian Gopopus, so CNRS researcher like myself, and he is the supervisor of Ziqiu's thesis.
Yeah.
Okay, so I let you start.
Yeah. And hello everyone. Welcome to my thesis defense. And today I'm going to present our research works during the past 4 years. Yeah. About the real-time performance in large-scale physical simulations. And let's begin the presentation. We all know that the surgical operations has significant practice, but they take inherent risk and potential complications. And to address these challenges, we can use the techniques of physical simulations from the community of computer graphics and biomechanics. And this allows us to replicate the anatomical structure in a virtual environment. And this helps us identify the potential challenges between entering the operating room. And nowadays, the physical simulations have various applications, such as the surgical planning and the training, the preoperative visualization, and the intraoperative assistant. And in addition, there are many other applications in the related fields, such as the robotics and deep learning. There are some of the general objectives of the physical simulations. The current focus in medical application is to integrate the technique with the operating room. For this, we need to fulfill both the requirements of the accuracy and the real-time performance. The real-time performance is very important in many of the applications, such as the surgical training, because we'll have a user that will manipulate the instrument, and we cannot predefine the behavior of the user. So simulation is not just play an animation, and we need to compute and return the relevant information to the user in a high frame rate. And in addition, we usually prefer the detailed model to capture more characteristics, and we also like that the simulation can deal with complex interactions, such as the contact and cutting. And to this requirements leads to many of challenges. For example, there are conflicts between the requirements of the high accuracy and the high computing efficiency. And specific problems will introduce further difficulties. For example, the nonlinear models in simulating deformable objects, the non-smooth problem in the contact problem, and sometimes we'll need to deal with the mesh topology modification when there is a cut. And our objective in this thesis is to enhance the computing performance such that we can enable real-time simulations on a large scale in the presence of the different interactions, such as contact and cutting. And my presentation will be in the following sections. First, I will introduce the state-of-the-art and the background of our research work. And then in the following 3 sections, I will present our contributions on the linear system resolution, the contact problem, and how to simulate a virtual cut. And finally, I will conclude our contributions, and I will discuss also some of our future works. And in the next section, we'll discuss the state-of-the-art. There is a considerable volume of physical and to simulate deformable objects. We have a various method. For example, the finite element method that follows the elastic models from the continuum mechanics. And there are also some other works, such as PBD, the position-based dynamics, shape matching, or mass spring. Some of them are very efficient, but not necessarily follow the physical laws. And in practice, in the medical applications, we usually choose the FEM to have realistic behavior. And an important choice in the simulations is the time integrations. We usually prefer the implicit Euler integration because it provides stabilities, also with the cost of efficiency. And to solve the dynamic equation, we have both the typical force-based solver and the projective dynamics that uses the local global alternating minimization solver. This method bridge the gap between the PVD and the finite element. But our work are still based on the typical force-based solver because many of medical applications are still based on it. And to solve the linear system, we have both the direct solvers and the iterative solvers. We usually prefer the iterative solvers in the real-time simulations because it has better control. Remember. And the contact simulation involves several problems. First, we'll need to search for the potential contacts, and this can be addressed by various collision detection algorithms. And then we have the contact model to define the nature of the interactions. To compute the contact response, we have the penalty method, which is very efficient, but only gives approximate solutions. And on the other hand, we usually prefer the constraint-based method because they are more reliable and guarantees the contact models. And to formulate the problem in the constrained space, we need to compute the compliance matrix, which can be addressed by different methods, such as using the augmented factorization, or using the approximation in the asynchronous preconditioner. And to solve the constrained problem, we have various methods such as the projected Gauss-Seidel and the non-smooth Newton. In practice, we usually use the projected Gauss-Seidel because it's efficient and simple to implement. And when it refers to the cutting simulation, we have the mesh-based method that are consistent with the finite element method. Using this method leads to many of challenges because we have the need of dealing with the mesh modification, and we usually need some advanced techniques such as the extended FEM that allows us to deal with the discontinuity after the cutting. And on the other hand, there are also meshless methods, for example, the material point method that has no need to deal with the mesh operations. But to keep consistent with the finite element, we're still based on the mesh-based method. And there are many of different ways to deal with the splitting of the mesh. And to cut an object, we have the mesh deletion, which simply deletes elements, which is very efficient, but we can see there are zigzags. And therefore bad quality of the surveys, and you will also lose some of the volumes. We have also the mesh refinement, which is very popular in the recent works, but it gives good quality of the cutting surveys, but it also generates many of the new elements and many of new connections, and it also has the problem of ill-shaped mesh. And we have also the node snapping strategy, which gives the good quality quantity of the cutting surface without generating new elements and new connections. And but using this technique meets many challenges, and we are going to address them in our method. And finally, we have an overview. Our research will focus on accelerating the computation in physical simulations, and we aim to provide efficient and accurate simulations. And we made our contributions mainly on the linear system resolution, the compliance, building of a compliance matrix in the contact problem, and cutting method using the node snapping strategy. And in the next section, I will present the background of the linear system resolution. First, before introducing the background, I will introduce the development environment of our work, which is based on the open source framework SOFA, which has an emphasis on medical applications, and it also supports software robot modeling. SOFA gives different types of physical simulations and various methods for specific problems. And it also provides powerful modules to accelerate the computation, for example, using the parallel programming. The parallel programming on GPU is very powerful. This is owing to the rapid growth of the graphic cards during the past 10 years. And in our works, there are many of the implementations that benefit from the high performance computing, which is very, very efficient. And this is owing to the massive parallel structures in GPUs. And however, using this technique also meet many challenges, such as the data transfer between the different processors and the learning curve. The finite element simulation is an efficient way to simulate deformable objects. And it actually factorizes the object into small problems. And each local element will follow the constitutive law from the continuum mechanics. We have the linear model, which is very simple and fast, but not suitable for large displacements and large deformable. And the real hyperelastic model is suitable for large deformations, but is very complex to solve. And in practice, we usually use the correlational model, which gives an compensation on the nonlinearity and provide a good compromise between the accuracy and the performance. And finally, by coupling all the local problems, the finite element gives us a global problem to be solved, which is actually an optimization on the total energy of the strain energy and the kinematic energy. In simulations, we perform time steps one by one and update the model positions at the end of the time steps, such that we'll have a visualization, we'll have an animation in visualization. And to follow the physical laws, we need to solve the elastic problem, which is actually equivalent to the Newton's second law, which describes an equilibrium between the external forces E here and the internal forces F. And depending with different definition of the internal forces F here, we have different time integration. Here, the explicit Euler integration use the positions and the velocity at the beginning of the time step, which is very efficient but unsuitable for large time step. And we usually prefer the implicit one because it's more stable and but also this more computation cost to solve. However, the implicit method usually meets the challenges on the computation cost. And for smooth animation, we need high frame rate, and which means that each time step should be small enough, and but this requires solving the nonlinear system with a very low computation cost, and therefore being very challenging, this problem. And for the implicit Euler integration, we have a first order approximation with the Taylor expansion, and this can be actually formulated as a linear system Ax equals b. And to solve this linear system, we have both the directed solvers and the iterative solvers. In real-time simulation, the direct solver is very accurate, but not suitable for large-scale problems. In real-time simulations, we usually prefer the iterative solver because we have a better control of consuming cost. And to solve the dynamic equation, we need to first assemble the system A and the B. A typical way is to explicitly assemble the system matrix. This method is very generic, but still needs some cost to assemble the matrix. And on the other hand, insofar we also have an implicit assembly method, which is very efficient but specific to several models. And I will give the details of the implicit assembly method, which is also called matrix-free iterative solver, in the next slide. In conjugate gradient algorithm, each iteration requires a matrix vector multiplication, which is the dominant operation in each iteration. And this operation can be actually factorized into local problems with the local stiffness matrix Ke. And GPU-based matrix-free solver was proposed earlier using a two-step parallelization. And this solver is extremely efficient, but is specific to the linear model and the rotational models. And moreover, because this GPU-based method depends on massive pre-computed data, which depends on the topology structure, it cannot be compatible with the topology changes. This is the main limit. And the preconditioning technique is a typical way to accelerate the convergence of the iterative solvers. We compute the approximation of the inverted system, and therefore we can reduce the condition number of the system matrix and accelerate the convergence. They are both simple and accurate preconditioners. An advanced technique insofar is the asynchronous preconditioner. We use a thread for the main simulation loop that runs the time steps one by one, and a parallel thread to execute a Cholesky factorization. This factorization is actually very costly and may cross several time steps. And once the factorization is done, in the main simulation loop, the factorized system is synchronized into the main simulation loop, such that we can use it to accelerate the convergence of the conjugate gradient. Here, in the linear system resolution, where we can use the approximation P, which remains a good approximation of the current system matrix, even after several times delay of several time steps. And in the next section, our objective is to I will introduce the background of the contact simulations. And For the contact model, we have the Signori's law to prevent the interactions between the different between the contacting objects, and the Coulomb's law to model frictional contact. Then, for the contact response, the penalty method can be used to solve the problem. It can be very simple to implement and being very efficient, but the main problem is that it cannot guarantee the Signori's law at the end of time steps, and such that contacts are only solved approximately. On the other hand, we have also the constraint-based techniques, which is accurate and robust for large time steps, and the interpenetrations are guaranteed to be eliminated at the end of the time steps. But this method also raises an augmented system, and therefore being very complex to be solved. And we'll look at the details of how to solve the constraint problem. First, we add a contact item in the dynamic equation. Then we solve it with free motion and the corrective motion. To solve the free motion, we solve the linear system without considering the contact item. Then we compute the Schur complement, which formulates the system in a constraint space. And this step is usually very costly because it requires inverting the system matrix with a large dimension and applied with the contact Jacobian H, which has multiple right-hand sides. And in the constraint space, the problem can be solved with different methods, as we have presented the projected Gauss-Seidel, the non-smooth Newton, and in practice, we usually use the PGS. And finally, we apply the corrective motion and integrate the system. We have an overview of the constraint-based method here. For the constraint-based method, it's not simply solving the dynamic equation, but should be accompanied with many of the other steps, from the collision detection to the corrective motion. And since we have introduced the asynchronous preconditioner in the previous slide, in fact, we can also benefit from this strategy in computing the Schur complement. As explained before, the factorized system can be used as a good approximation of the current system, even with a delay of several time steps. And therefore, we can compute the compliance matrix with this approximation. And this can be achieved by a two-step implementation. This two-step implementation can be achieved in a GPU-based method. Insofar, it consists of two steps. The first one is a sparse triangular system with multiple right-hand sides. This is very costly because there are many of data dependence, and the step two is easy to be processed in parallel in GPU, and therefore it can be very efficient. In the step one, to solve the triangular systems, we have a two-level parallelism. The resolution of each right-hand side are independent from each other. Therefore, we can put side. The left-hand side L is still full processed. And with the background, we make a workflow of the physical methods with different steps. And now I will begin to present our contributions. The first section is about the linear system resolution. we have proposed a fast assembly method and an efficient numerical solver. In the linear system resolution, we have introduced both the advantages and the drawbacks of the matrix-free solver and the matrix assembly. Our objective is to provide a generic and yet very efficient solver. For this purpose, we proposed a fast matrix assembly strategy. First, let's look at a typical method of matrix assembly. We first collected the information from the mesh data, and this actually formulates a triplet set which contains the indices of row and column and the values that are to be added in the final matrix. And then with the sorting and the compressing stages, we can finally store the data into a compressed format, for example, the compressed sparse row. And here, here we have the typical way is very costly, mainly because the sorting and the compressing stages. And here we have an important observation that suppose that we have no topology change during the simulation. And in this case, we know that the sequence of the adding of contributions will not change. And supposed to build a deterministic mapping from the triplet set to the uncompressed format value. Oh, yeah, there's echo. And it's okay? Okay. And when processing the assembly, we can directly build the uncompressed value using the deterministic mapping. And this actually allows us to skip the costly sorting stage. And for the compressing stage, we can use the parallelization either on the CPU or on the GPU. And here I will give an evaluation of our new method. First, when the mesh topology is not changed, we have saved a 70 log assembly cost by using the deterministic mapping. And on the other hand, when there is a topology change, our method combined with the CPU merge still remains the same level of assembly cost. And the GPU merge will be more costly because there will be data transfer between the different processors. We also compare our methods with the matrix-free solvers in SOFA. It has been proven that our method is very generic for different models and also very efficient. Also, we have an obvious drawback of the fast assembly method that once there is a topology change, we can no more use the deterministic mapping to accelerate the process. We will present later an enhancement fast assembly method combined with our new proposed cutting method in the following section. Then in the linear system resolution, we have also improved the performance in the numerical solver by upgrading the Cholesky preconditioner. A challenge in the preconditioned solver is that we have a CG fully based on GPU, but but a CPU-based preconditioner. This is mainly because the triangular systems are very difficult to be parallelized. This due to the massive data dependency, and this actually causes massive data transfer because the process the operations are running on different processors. And for this purpose, we propose the GPU-based preconditioner using the domain decomposition technique. The tasks on the same level here with the same color marked in the figure will be processed in parallel. And with this implementation, now we have a GPU-based preconditioner. So we have a fully GPU-based CG preconditioned conjugate gradient now. And we have also compared our new proposed preconditioner with other typical implementations. Compared to the NVIDIA's CUSPARS implementation, the previous GPU implementation, the CPU implementation, our method is noted as a GPU ND. ND is the nested dissection for the graph partitioning, has been proven to be very efficient and here have a speed up compared to the fastest implementation. And in the next section, our objective is to remove the critical obstacle in the contactor problem. First, let's look at the time consuming in the constrained problem. We know that even using the asynchronous preconditioner, even the factorization has been removed from the main simulation loop. Even with a GPU-based implementation, the short complement is still very costly, and it will take 80% of the whole time step, and in the large-scale problems. And this has been the main obstacle in the contactor problem, and accelerating this step will be necessary, and we'll propose a new method for it. First, let's consider an example. Imagine that a deformable raptor mesh is contacting with a rigid plane, and we can see that the contact zones usually focus on local areas such as feet. And we have the constraint Jacobian that propagates the constraint space C to the mechanical motion space N. And generally, the constraint Jacobian matrix is very sparse because only a part of the mechanical dots, the degree of freedoms, are impacted by the constraints. And based on this observation, we propose to separate the information in the contactor Jacobian. We first collect all the non-zero rows in the Jacobian, and then we eliminate all the We first eliminate all the non-zero rows and formulate H hat here, and then we collect all the non-zero rows in H transposed here and formulate a partial identity matrix. And by doing this, we generate a new dimension K, the isolated dots dimension, which are actually the dots impacted by the constraints. And the relation between the new generated matrix can be actually expressed as matrix multiplication. And the partial identity matrix I bar here has some special properties. It takes one and only one element on each column, and there's no value information in the I bar because all the values are set as 1. Then with this reformulation, we modify the original in GPU implementations. For the step 1, the triangular system, now compared to the previous solution, owing to the special property in the right-hand side, now each right-hand side holds only one only one value, and following the elimination tree, only the elements that depends on the dots here, the only elements will need to be processed, and this needs to a very sparse resolution, and such structure for each mechanical dots index can be pre-computed, since the elimination tree only depends on the mesh topology structure. And we propose to pre-compute all the structures for all the mechanical dots offline. Then we can compare the solvers before and now. In the previous implementation, the matrix was fully processed, and it was hard to predefine the pattern in the right-hand side offline. And now, with our new method, we are released from the different combination of the value in the right-hand side, and therefore it allows us to process a structure which can be very efficient, and this structure can be predefined with the elimination tree. And for the parallelization, for the right-hand side, the principle is the same as before. Each one will be processed in a dedicated multiprocessor. Then we evaluate the performance in different conditions. Compared to the dense resolution, our sparse resolution now has a significant speed up to 50 times speed up from the dense resolution. We also proposed a reuse strategy to further accelerate the computation. Let's consider an example. A deformable lever mesh is contacting with the rigid plane, and we have an observer. As time goes on, the contacting area will change, and this is the same case for the dots impacted by the constraints. And we have an observation that in between the consecutive time steps, they usually shares many of dots impacted. For example, here we note them as the blue points, and for the red points, they are the new dots impacted that emerges in the current time step. Then we combine this observation with the asynchronous preconditioner. Imagine that from time 2 to 6, that corresponds to the bottom frame. In this case, the main simulation loop keeps using the same factorized system, and the L is not updated. Then we solve the triangular. When we solve the triangular system, we have the blue and the red dots impacted by the constraints, and because for the blue ones, they have the same left-hand side L, and they have the same right-hand side, so they have already the shared solutions. This means that for the blue impacted dots, we have already the solutions in the GPU memory, and we have only need to process the red ones, and therefore the system dimension could be much smaller. And owing to this, we have the reuse strategy, and we have also compared the method with the standard one, the standard sparse resolution, and we have a further speed up compared to the sparse resolution. Now, we have also made a comparison with different solvers. Now we have a speed up of nearly 100 times speed up compared to the previously fastest solver in so far. And now with our new method, we successfully removed the obstacle in the contact simulations. The short complement now takes only 5% of the full time steps without changing any other parts in the simulation loop. And more importantly, our method's sparse resolution, the reuse strategy, holds the same accuracy to the dense process. The only approximation we have used is using the approximation in the asynchronous preconditioner. And here are some interesting animations using the software robot. And we have also integrated our method in the application of the needle insertion animation. The reuse strategy has been proven to be very efficient since all the previous inserted part can benefit from the strategy of reuse. And in the previous sections, neither the fast assembly method nor the efficient contact solver, the sparse resolution, they all depends on the pre-computations of pre-computed data that depends on the mesh topology. Therefore, they cannot naturally deal with the topology changes. We would like to overcome this drawback in the cutting simulations, and therefore we propose a new method of virtual cutting. And to keep the numerical resolution efficient, we don't want add considerable new connections during the cut. Therefore, we choose the node snapping strategy that only splits the mesh from its existing surfaces, and also good for cutting surface without generating new elements. Our objective, we want to achieve the interactive cutting with the user's manipulation, and to keep stable and efficient, we would like to optimize the mesh quality and the performance. But these requirements will give us many of the challenges. For example, the ear-shaped mesh. Here, in the original method, since we only snap the nodes nearby the cutting path, we will generate the ear-based elements. Then we have some problem of energy preservation, and in the progressive cut, we cannot predefine the cutting path, and this makes it also very difficult to search for the splitting boundary. And in addition, in medical applications, there are also potential perturbations. For example, the holding of instruments by a user can hardly avoid small vibrations in the practice. And we have also, finally, we have also the problem of dealing with topology change in the efficient numerical solvers. And we have proposed the corresponding solutions for these challenges. First, for the ear-shaped mesh, we have proposed the original method only snaps the nodes nearby the cutting path, and now we propose them to process an elastic snapping that will that all the mesh nodes are snapped. by the elastic forces. And this process actually optimizes the mesh quality after cutting. And solving this problem can actually be formulated as a bilateral elastic problem, which uses the constrained problem. And in this case, we can use the method, the sparse resolution we have introduced in the last section to accelerate the computing. And the reuse strategy can be also used because the already cutted parts, snapped part can benefit from the acceleration. And after snapping, it will be necessary to update the initial stiffness matrices. We propose to set a threshold to only snap the nodes that with enough displacement such that we avoid updating all the elements. Then we have the problem of preservation of energy combined with the elastic snapping. And imagine the problem of preserving energy is if we fix the nodes after snapping in the deformed shape, it will lose the ability to restore the reference shape after fixing. To address this problem, we propose to conduct a virtual simulation and process the snapping in the virtual simulation with a replicate of reference shape of the actual simulation. Once the object is snapped in the virtual simulation, we modify the reference shape of the actual simulation and such that the mesh will have a tendency to fit onto the cutting path. Then to compose the cutting path in progressive simulations, we record the interactions between the object and the instrument and store the result in the format of point cloud. Then we use the moving least square method to smooth the point cloud and finally generate the cutting path mesh after triangulation. In the progressive cutting, it's difficult to keep consistent with the previous cut. To make sure of the consistent, we propose the efficient geometry operations to search for the splitting boundary. The main principle is to compute the interacted subtopology, the green part, and by choosing one of its surveys, we have the splitting boundary that is guaranteed to be consistent with the previous cut. And as we have presented in the previous slide, the matrix-free solver is not compatible with the topology change since it depends on massive pre-computed data. An important property of our new method is that new cutting method is that the splitting of mesh is along its existing surfaces, so that will be no additional connections after cutting. Based on this property, we proposed an efficient update of the pre-computed structure of GPU structures in the original matrix-free solver. And with this enhancement, now the matrix-free solver is able to deal with the topology change. Here, we show the workflow of our new proposed method. Our first step is to detect the interactions between the instruments and the object to cut, and this results in point cloud. Then with moving least square smoothing, and after triangulation, we will generate the mesh, cutting path mesh, the red line here. And by searching for the interacted subtopology, we have the splitting boundary that will be snapped onto the cutting path after an elastic snapping. And this process actually optimizes the mesh quality after snapping. And then we apply all the displacement in the reference shape of the actual simulation, and finally split the mesh with the splitting boundary. And we show here the process visualized in SOFA framework. Here, the generating of the cutting path, searching for the splitting boundary, and the boundary is snapped onto the cutting path. And finally, in the actual simulation, we split the object. And we also applied our method in some other interesting examples. The first one is with a user-defined cart, and the second one shows the ability of preservation of energy. And we also evaluate the computing performance. We give all the details of performance in each stages, and the actual and virtual ones, with the example in different discretizations. We also evaluated our proposed solver and the enhancement to the matrix-free solver. Now, with our efficient update of the pre-computed data, it remains very efficient even in very large scales. And with an example, we evaluate the mesh quality after cutting. Here in the left figure, we show the evolution of the vertex number in progressive cutting. The different curves represent the different discretizations. Here, for example, we have a 9,000. We have a 9,000 of nodes, initial nodes, and it will increase as the time goes on, as the cutting is going on. And in the right figure, we have the condition. We have the same evolution of the condition number. And in both of the figures, we can see that the increase of the vertices number and the condition number is a measure of mesh quality. Both of them are limited. And finally, I would like to have a conclusion of our contributions in this thesis. We have proposed an efficient method for matrix assembly and an upgraded Cholesky preconditioner that enables us a full GPU-based preconditioned conjugate gradient. And in the contact problem, we have proposed an efficient reformulation for the short complement. And now we have a very fast computing of the compliance matrix. And finally, we have the proposed dynamic cutting method that with mesh quality optimization and an efficient enhancement to the matrix-free solver. And in this thesis, we also proposed some perspectives, and which are potential future works, but remains developments. The first one is an implicit constraint resolution that where we can update the constraint direction during the PGS iterations. And we have Claire in the team that follows this subject. And we also have proposed an enhancement to our faster matrix assembly method to efficiently update the deterministic mapping to make it compatible with the topology change. And with a similar principle to the asynchronous preconditioner, we have also proposed an asynchronous cutting strategy, which removes the cutting process from the time step main simulation loop and update the topology change in a low frequency. And finally, we have also discussed some enhancements of updating the compliance with in the case of topology change. And that's my presentation today. Thank you very much for your attention.
Okay, so thank you very much for your presentation. It was a bit longer than expected.
Oh, sorry.
So it's time for questions, as usual, and we usually start by reporters. So we can start by Christian if you want, if you don't mind.
It's okay with you if I start, Stefan?
He smiles, so I guess
it's okay. Okay. Thank you very much for your presentation. It was very, very interesting work and very interesting presentation. I think like the presentation you did today was a little bit longer than what it was expected, but at least it was, at least in the way you presented things were, I think there were some things that you learned from, like maybe the critics we did on the manuscript, which I think was very good in terms of science, but not so much in terms of presentation.
Yes, I'm sorry, I'm just a little nervous.
Really, I think this work is very interesting. It's following what we have done several years ago with Adrien. And you obtained very, very impressive results. So congratulations on that. I have some questions, remark and questions maybe. So maybe like some precision concerning the background.
Yeah.
You said that in a real-time simulation we usually prefer iterative solvers.
Yeah.
I would half agree with that because somehow with the iterative solver you are not sure of how many steps you will have to need for convergence, whereas with the direct solver there is less change in terms of computation time.
Yeah, that's true, and that will depends on the system scale. For example, with a small system, we can use the direct solver, which will not take much of time computing cost. But especially in large scale problems, to control the time consuming there, it may be better to use the iterative solver. I agree with you for the expression I made.
and basically, in fact, I have several questions on that actually. So,
yeah.
Because in fact, as you said, depending on the size of your mesh, maybe in some case it could be interesting to basically not
time performance for large scale. We want to simulate in real time so directly using the Cholesky factorization in a time step, because that will cost the most part of the time step, of the animation loop.
So of course there was a lot of background in your work, and
yeah.
You I think a good job. It's not easy because you have to go back to what has been done. And in the background, you present the fact that we use the computation of compliance when we are using constraint-based approach.
Yeah.
But in fact, that's not really mandatory. Right? You can use constraint-based approach.
Yeah, we have also penalty method. We have also.
You can even use Lagrange multiplier.
Yeah.
And in fact, compute the result of your Lagrange multiplier
Sorry, I don't get it.
I mean, you can build a system with your language multiplier.
Yeah.
And you can basically you can solve the matrix with the
Yeah, sure, we can. Yeah, in the non-smooth Newton, I think they did like that. Yeah, that assemble a full augmented system and solve it with some specific methods.
So yeah, maybe this I think yeah, just because the presentation is
Complementarity